Well, hello there. We're going to have a look at reciprocal circular functions. A fascinating little topic. These are the 1/overs, 1 over sine, 1 over cos, and 1 over tan. So let's get started and have a look. Okay, reciprocal function number 1. That is cosecant. It's called cosec x for short, and it's 1 over sine x, providing, of course, that sine x is not equal to 0, because it wouldn't be defined then. So that's telling you something, isn't it? It's going to have some asymptotes because sine does get to 0 in certain spots. So there's sine. Okay, we're going from naught. Actually, we're going from. What are we doing? Oh yes, we're going from 0 to 2 pi. Yes. Now, what I've done here, ladies and gentlemen, is I've basically shown you the point where sine equals 0 there, because that's going to be an asymptote for cosec, isn't it? Because 1 over 0 is undefined. That's why I drew that there. It just confused me for a moment. I thought I was drawing an axis, but it's not. It's just it's the asymptote of cosec. This is where the origin is over here. Now you think to yourself, what would the reciprocal function look like? Okay. Now this is where sine equals 1. So the reciprocal is going to be 1, isn't it? This is where sine equals minus 1, so the reciprocal is going to be minus 1, yes? Where sine is positive, the reciprocal will be positive. Where sine is negative, the reciprocal will be negative, and so on and so on. Have you got it worked out? Because I'm going to reveal it to you on the ready, set, go. Alright? Have you got it? Alright, good. Ready, set, go. There it is. There is cosec in all its glory, okay? It's pretty amazing, isn't it? So it has asymptotes here where sine equals 0, and here where sine equals 0. That'd be an asymptote there where x is 0, another one where x is pi, another one where x is 2 pi. Yes, can you see that? Yes, it's pretty straightforward, isn't it? Alright, so therefore I've just drawn the vertices in there for you, just so that you'll get the full picture. That's pi on 2 and 1. And that's 3 pi on 2 and minus 1, okay? And that is an asymptote, yes, x equals pi. And the range of cosec, as you can see, is basically from minus infinity to, wait a minute, I've got to fix something up, to minus 1. I just had a 1 in there by mistake. So minus infinity to minus 1, or 1 to infinity, and those 1s are inclusive, okay? So it's not defined within this no man's land from sort of there up to basically up to there, right? Up to where from minus 1 to plus 1 y values non-inclusive. Yeah, you get that? Alrighty, so that's cosec, the first star of the show. Let's keep going. What do we got? Secant now. Secant, you will find, sorry about that. We've got sec equals 1 over cos, provided, of course, that cos doesn't equal 0 and cos does equal 0 at certain spots, so that sec is going to have asymptotes as well. And considering, ladies and gentlemen, that cos is just basically the graph of sine, but out of phase by 90 degrees from sine, it'll look very much like cosec. There's sine, there's cos, I'm trying to say, and that's a potential asymptote for sec. There's an asymptote for sec, because that's where cos equals 0, so pi on 2, x is pi on 2, and x is 3 pi on 2. Now, you ready for this? I think you've probably got it now, because it's very similar to what we saw on the last screen. Right? And there's the vertices for you, 0 and 1, pi and minus 1, and 2 pi and 1. And so what are we saying? They're asymptotes. Pi on 2, x is pi on 2, x is 3 pi on 2. And the range of sec is minus infinity to minus 1, or 1 to infinity, and the 1s are included, just the same as cosec was. Alright? Yes, very good. Okay, here's the third one, cotangent. Now, this is 1 over tangent. It's called cot for short. And yes, provided tan doesn't equal 0, which it does in certain spots, so this is also going to have asymptotes. Now there's the graph of, what's that the graph of? That's the graph of tan. That's the graph of tan. Now, tan already has asymptotes anyway at pi on 2 and 3 pi on 2, but cot. Now, the funny thing is about cot, look, cot has asymptotes where tan equals 0, because you can't divide by 0, 1 over tan. So it would have an asymptote there, it would have an asymptote there, and it would have an asymptote there, alright? And with reciprocals, where something's very large, the reciprocal is going to be very small. So when you get up here into the realms of infinity, this thing becomes so small, cot becomes so small as to go through 0, right? So there's going to be a 0 there when tan is undefined, and there's going to be a 0 there when tan is undefined. Let's reveal all. Have you got it? Oh, there it is. It's a beautiful piece of work, isn't it? And the other thing is, where tan is 1, the reciprocal will be 1, that's cot will be 1, and then that happens where y is 1, right? So that's what cot looks like, alright? There are the intersection points that I've drawn there for you, because this thing doesn't have really any vertices, it's just, you know, goes off berserk into outer space all the time with all these asymptotes. And the what would the range of cot be? What would you think it would be? Yes, well, there's the asymptotes, pi on 2, 3 pi on 2. The range of cot is all real numbers, because it just goes down here to infinity, goes up there to infinity, and that's what it does. Yes, good show. Alright, now we're going to sketch. Now this is where it gets a little bit knotty. We're going to sketch more of these trigonometric graphs, which does drive students quite crazy, because it's considered to be very fiddly and a bit annoying. However, the good thing is that you really never get these to sketch in the exams as a sort of a sketch the graph kind of question. What they usually do is give you multiple choice questions where you have to work out something about the transformation of a sec or cosec or cot graph as a multiple choice question, which means it's short, punchy, you have to know what you're doing, and the answer is really quick, rapid fire. But it behoves us to sketch a few just to broaden and deepen our understanding of, you know, sketching trigonometric graphs, so that we can then do those multiple choice questions properly when they confront us, because we've only got 1 minute and 40 seconds to answer each of them, which isn't very long. So I'll stop rabbiting on. We're going to do the first one. This is cosec of 2x. Now, look, what you do, guys, is don't melt down because of cosec or sec or cot. You just basically, for cosec you would do sine, and then from sine you can construct the reciprocal function as we did on the previous screens. So you would draw y as sine 2x, and then you would basically go from there. Now, the period of that is pi, so you get 2 complete cycles in 2 pi, okay? That's sine 2x, isn't it? Now, we can construct the cosec 2x from that. It's just going to go like that, and so on. It's going to go there, and it's going to come in and meet the thing where it's 1 or minus 1. You get the idea, don't you? So there it is. Yeah? Excellento. Very good. Yes, I've just drawn in the vertices as the intersection points. Everything's good. I've done the equations of the asymptotes, haven't I? For cosec, yes, I've written them in. X is pi on 2, x is pi, and x is 3 pi on 2. Make sure you do that if you're doing sketch graphs, otherwise you lose marks. Very important to do that. Oh yes, very good. All is good. Now we're going to do sec of x minus pi on 3 from 0 to 2 pi, which means that we've really got to start off doing cos of x, because sec is 1 over cos, then do cos of x minus 3, and then do the sec bit after all that. Now, there is, that's straight cos, going from 0 to 2 pi, right? I've just got this happening over here a little bit as well, but don't pass no remarks about that for now, because I'm going to do a really rabbit out of a hat trick here for you. See, for this beastie here, you've basically got to, that means that you've got to translate the whole graph to the right by pi on 3, wouldn't you? But that's a lot of trouble, guys. So what I do is a little wolfy trick, is I move the axes, the y-axis, to the left, which is the same thing. It's all relative, isn't it? So that's what I do. I start with y equals cos x, and that's why I've got this little bit of extra region up my sleeve here, because I'm going to move these axes back. And you'll see with great wonderment what will happen. So y is cos x. Okay, so we're going to, yes, we either move the graph forward by pi and 3, which is an awful lot of trouble to do, rubbing out things and, you know, doing it all again, or we just move the y-axis back by pi and 3, which is easier. All right? Watch. Watch this, my children. 1, 2, 3, 4, kaboom! Oh, it's a very nice little trick, isn't it? Now this changes everything, right? This is now the new y-axis. That point there, this I've done this scale as 12ths just to sort of so we can see what we're doing, and therefore pi on 3 is 4 notches, 4 pi on 12, yeah? So that makes this a new everything, basically all these values now. That was the old origin, wait a minute, where was it? 1, 2, 3, it used to be there, that used to be the origin, right? So that's now pi on 3. Okay, so everything's got to be recalculated, and then you recalculate and label the scale, the intercept, and the endpoints, and then you remove the redundant parts of the graph, like you don't want that bit anymore, and half of this won't be required anymore because 2 pi is now here, isn't it? Yeah, that's right, because we moved the axes back, so that's going to become, that old point there on the very end used to be 2 pi, but it's now 2 pi plus pi on 3, which is 7 pi on 3. So that just means you just got to recalculate the axis, but I think that's easier than moving the graph. There it is. I've done it all in one fell swoop for you. Alright, and then what I've done then is I've done the reciprocal bit there, okay? So that's the sec, that black curve is the curve of the sec bit. Alright? Yeah, and yeah, well actually that should be going up there. Look, can you just imagine this going up here as well? Like that. Actually it won't be joining, it'll be starting there, and it'll be going up like that. Like that, yeah? Down to there somewhere. Yes, okay, so that's what it looks like. Actually, I just paused the video and fixed it up for you. It's going to be the sec's going to be up here. It's so because when this is 2 pi and a half, this will be 2 pi and 2. So it's just zooming in, like Halley's Comet coming in here for a rendezvous with the cos graph, and the other one's up here. That's 0 and 2, because that's going to be 0 and a half. Okay, that'll be an intercept there, right? That'll be a y-intercept at 0 and 2. Okay, so that fixes it up. I had just forgotten to do that, so my apologies, but it's right now. Okay, let's go. Now we're going to do cot of 2x plus pi on 4. Okay, well that's interesting, isn't it? So it looks like we better do tan of 2x plus pi on 4, which probably means we need to do tan of 2x and then translate it to the left by pi on 4, right? And as it happens, that because the period of tan 2x is basically pi on 2, then pi on 4 is going to be exactly half a cycle. So that's going to be nice and neat for us, okay? Now, firstly the graph of tan 2x, then the graph of tan 2x plus 4, then from that we can do the cot bit, right? Now, this is going to be very busy, so I'll give you fair warning. The period of tan of 2x is pi on 2, yes. We have a horizontal translation of pi on 4 to the left, yes. To achieve the horizontal translation, we can move the y-axis to the right instead of moving it to the left as we did in the previous example for sec. Okay, to where x is pi on 4, we're going to move it to the right to where x is pi on 4 in this case. So here, then extend the graph beyond the right hand end by another pi on 4 to get to x is 2 pi again. Now that's what I'm trying to say. That's the graph of, now wait a minute, that's looking a lot of very busy. That's 2 pi. So instead of having, yeah, that's right. So I've got the graph of tan 2x there because there's exactly 1, 2, 3, 4 cycles there instead of 2 in 2 pi. So therefore the period of that thing must be pi on, not pi but pi on 2. Yeah, that's right. Therefore you get 4 of them in 2 pi. Are you right now? Apple of my eye, Mr. Pi. So here we go now. That's the new axis there. That's the new axis where x is pi on 4. That'll be my new y-axis if I'm going to move the axis forward, right? Now, stand by, guys. I think I've got the new graph coming in for you. oh no, that's the new y-axis, and I'm going to extend that by another pi on 4 to make the new 2 pi point, because I've shortened the graph a bit by moving the axis this way here, so I need to make it grow a little bit by pi on 4 that away. Yeah, here it comes. Graph of tan 2x plus 4. Come on down. Whoa, look at it. So there it is. We've got the graph of tan 2x plus 4 from x is 0 to 2 pi. Now, okay, this is what it looks like. So there's 1, 2, 3, 4 cycles there, okay, and this, basically this axis has been moved over, okay, over to the right by pi on 4 compared to what it was before. Now, that's very busy, isn't it? So what I've actually done there is I've drawn in all the asymptotes of tan, this one, this one, this one, and that one, but I've also drawn in all the zero, because they're going to be asymptotes of cot, right? So pi on 4, 3 pi on 4, 5 pi on 4, 7 pi on 4, right? They're going to be the asymptotes of cot. Now, watch this, guys. There it is. There's cot. It's amazing, isn't it? It's very busy. I told you to be busy. Now, let's just try and make some sense out of this. Okay, that's the graph of h of x equals cot of 2 times bracket x plus pi on 4. And when tan equals 0, cot is undefined. Do you get that? Do you see that? See, tan's approaching 0 from the positive, then cot is undefined in the positive. When tan is approaching 0 from the negative, it approaches minus infinity from the negative. That all makes sense. The other thing is when cot equals 0, tan is undefined, right? Same deal, okay? So when tan is undefined, cot becomes 0. You need to know that. The other thing is the curve. Yeah, the curves cross swords. This is the way I like to think of it. It's like crossing swords. I'll colour a little bit of it in for you to see what I'm talking about. That's what it looks like, right? And basically the cot is like a backwards tan, and the swords cross when y equals 1, right? So what you do is you draw the tan asymptotes, then you draw the cot asymptotes where tan equals 0, and then you basically cross swords with the tan between the asymptotes, both above and below the horizontal axis, right? And they cross swords where y equals 1. That's the way you draw cot. Okay? That's how I figured it out after a lot of misery trying to work all the symmetry of it out, yes? Okay, that's very good. Now we're going to find the for something completely different. We're going to find the exact value of each of the following. Very interesting. Well, look, there's no problem with that. All we need to do for this one, we'll just do it for tan first, and then just do the reciprocal. For this one, we'll do sine, then find the reciprocal. For this one, we'll do cos and find the reciprocal. So we're just doing the old circular function routine here, no problem. So first of all, work out tan of 11 pi on 4 and then take the reciprocal. So what we've got to do is say, well, 11 pi on 4 is 8 pi on 4, which is 2 pi plus another 3 pi on 4, so it's actually effectively tan of 3 pi on 4. Now, you know what tan 3 pi on 4 is. For goodness sake, of course you do, after all this time. Basically, it's going to be minus 1 because it's in this quadrant here. And tan is negative in that quadrant. It'll be the same as the quadrant 1 value of tan on pi on 4, except it'll be negative. And tan of pi on 4 is 1. I hope you knew that. Yes, so that's what we're going to get, minus 1. Therefore, cot is going to be minus 1. Right, that's very easy, isn't it? Yeah, so you don't need to worry about these. These are very simple. What about cosec of minus 11 pi on 3? Firstly, we need to do sine of minus 11 pi on 3, and this is, for my next trick, this is the way I'm going to sort out this negative. You should know that sine of a negative angle is minus the sine of the positive angle, because sine, ladies and gentlemen, is an odd function, right? Is an odd function. And if you don't know what I mean by that, you better ask someone, right? Basically, it means that what's to the left of the y-axis, if you think about it for sine, what is to the left of the y-axis is going downwards, just immediately to the left of the origin. What is to the right of the y-axis is going up. So the sine of a negative angle is always the negative of the sine of the positive angle. you better wind the video back and play that 5 times if you didn't get that. But you need to know that. That's just absolutely crucially important information. Now, 11 pi on 3, let's just massage that a bit. That's 6 pi on 3 plus another 5, so that's 2 pi plus 5 on 3. So we're really looking at the sign, minus the sign of 5 pi on 3. Remember, we're doing minus the sign of 5 pi on 3. Now, what's 5 pi on 3 on a good day? Wait a minute, it's just pi on 3 short of 2 pi. So therefore it's going to be the same as the sign of pi on 3, except it's going to be negative, isn't it? I think. Yes, that's right. Sine of pi on 3 will be negative sine pi on 3. And sine of pi on 3 is root 3 on 2, so it's going to be negative root 3 on 2. Therefore, we're asked for cosec, therefore it's going to be negative 2 on root 3. Yes? Excellento. Excellento. So, uh-oh, we made a blunder. Did you see where I went wrong? No, I'm not going to admit to whether I made it by mistake or deliberately to trip you up, because I need you to be watching here. Look, I said that sine of 5 pi on 3, right, I said that equals minus root 3 over 2, yes? That's correct, isn't it? But basically we are trying to find this, which is basically minus sine of, effectively, 5 pi on 3. So we're trying to find minus it. So I've basically left that minus out. So basically this has to be minus sine pi on 3, because it's minus sine of 11 pi on 3. So there you go. That's not right. So I'll just pause the video and fix it for you. There it is. I fixed it there, right? It's there. So it's actually plus is the answer, okay? So yes. Do you understand what I just did? Well, if you don't, just have another look at it and you will get it, okay? It's basically, this is a quadrant 1. This minus 11 pi on 3 puts you into quadrant 1. Basically it does. If you whirl around the quadrants, going in the negative direction, backwards by 2 pi and then another 5 pi on 3, you'll find that you'll end up in quadrant 1. So we need a positive answer. So don't fall in the fat like that and come out, as we used to say when I was a kid, don't fall in the fat and come out dripping, or end up in the algebra ditch. Now, where are we now? Right, the next one. Firstly, we've got to get, for this one here, this one up here, we've got to get cos of 11 pi on 3. Alright, cos of 11 pi on 3 is the same as cos of 5 pi on 3. Cos of 5 pi on 3 will be the same as cos of pi on 3. Is it? Wait a minute, just work that out. Just zooming around here like that. 5 pi on 3. That's 1 2/3. Yes, because this cos is positive in that quadrant, right? So that's going to be the same as cos of pi on 3. Cos of pi on 3 is a half. Therefore, we want sec. Sec will be 2. Yes for me and you. Yes, that's great. Alright, you okay? Good. Now, 2 new identities for you today. We know, now this is very important, these are for specialist maths, these ones, exclusively for us. We know that sine squared x plus cos squared x equals 1. Well, I hope you know that. That's the fundamental, I call it the bread and butter theorem of trigonometry. It's so important. Now, what we're going to do is we're going to massage that a bit. We're going to divide both sides by cos squared x. And we're going to get that, okay, and that's going to turn into tan squared x plus 1 equals sec squared x, our new star performer, the reciprocal function here squared. Okay, so you need to know, that's one that you need to know. 1 plus tan squared x equals sec squared x, which is really important. And secondly, we're going to take this bread and butter theorem up here again, and we're going to divide both sides not by cos squared this time, but by sine squared, and we're going to get something different. There it is, and it's going to be 1 plus cot squared x equals cosec squared x. Gracious me, wonders never cease, and that is the second really important extra theorem that you can derive both of from the sine squared x plus cos squared x equals 1 theorem. These need to be, they're very useful, they need to be learned. Don't just put them on a cheat sheet and hope to use them if you need to use them. You have to have them in your head so that you recognise things when your eyes hit the page. Otherwise your eyes will hit the page and you won't know what's going on, you'll waste all your time. For example, if we wanted to simplify the expression cot x over cos x minus cos cubed x, the way you could simplify that, these are these proof things. They're rather marvellous, but it's not a proof, it's just a simplify in this case. So I think my instinct tells me I could simplify that by making cot 1 over tan, which is cos over sine, isn't it? Yeah, that's right. Now, that's pretty interesting, isn't it? So what we can do now is we could cross the coses. There's a cos up here, and there's a cos down there, which I think we can cross out like that. So what do we end up with now? We end up with, oh yes, and also 1 minus cos squared x is sine squared x. So it looks like we've got cosec cubed x. My goodness, that's pretty good. Now I think we've got oh yes, here's another one of these things. These things always crop up, and they're really, really easy to do if you use what I call, you don't need to use the identities. In the textbook that I use, they tend to use the identities to work these out, but I don't like using the identities. I use what I call the magic triangle. Okay, so what are we talking? Tan x equals 3, which means that we could be in quadrant 1, or we could be in quadrant 3, couldn't we? That's where tan is positive, so we've got a choice here. We don't know which quadrant it came from because they didn't tell us. So we're going to find out, yes, we're going to find out cosec, sine, cos, and sec of x. Now, here's the magic triangle. This is really a star performer, this little guy. He's marvellous. So you basically say, okay, x has a tan of 3 over 1. 3 over 1, right? So therefore, you can use Pythagoras' theorem to get the length of the hypotenuse, which would be root 10. Now, you just read them off. You just read them off, guys, but then you go back to your cast diagram to work out whether what the sign is, I mean the SIGN sign, whether it's going to be plus or minus of whatever you get, by looking at the cast diagram. So let's go for the first one, which would be cosec. Now, cosec being 1 over sine, sine being 3 over root 10 now, therefore cosec is going to be root 10 over 3. However, is it going to be plus, is it going to be minus, or what's it going to do? Well, if it's in this quadrant here, it's going to be plus. If it's in that quadrant there, sine will be negative. So cosec x could be plus root 10 over 3, or it could be minus root 10 over 3, couldn't it? Yes, okay, here comes sine now. So sine would be just, that's easy to do after we've just done cosec. Okay, so similarly, sine will be 3 over root 10 or minus 3 over root 10. That's easy. Now what's next on the agenda? Cos, is it? Right. Cos x. Now cos x is going to be, if you look at this little magic triangle, cos x is going to be 1 over root 10. So therefore, if it's in this quadrant, it'll be plus. If it's in this quadrant here where tan was positive, also cos will be negative. So we've got 1 over root 10 or minus 1 over root 10. And now we can just reciprocate that, pardon the English, to get sec. Sec would be root 10 over 1 or minus root 10 over 1. That's it. And that's the end. So did you see the light? Well, you'll be right if you saw the light. And that's the end of our wonderful little video on reciprocal trigonometric functions. The stars were cosec, sec, and cot. So, thanks for listening. Have another look if you're not sure of any of it, and practice some of those, sketching some of those trig graphs. That's really good for you to practice those, because they're tedious and complicated, but they really sort your head out on what you're doing. And then you'll be able to answer those multiple choice questions, which is what they really ask you in the exam, competently and well. Okay, see you in the future. Bye for now.